blue Samsung phone that we found, and we know the name of the person that owns it because their wife called. They're looking for you. But if you're looking for your phone, we have it at registration.
Great, thank you. Right, I've got the mic, I've got the slides. This is going to be about a scientific paper that scooped another scientific paper that we wanted to write, and how we basically got back at it. I'm RogueAP Bratus. I'm a research assistant professor at Dartmouth College. This is Anna Shubina. She is the math brains of the operation. There's also a student who actually did all the work as it goes, Chrysil. He unfortunately could not make it today, but we'll go through his part as well. And with that, let's start it off.
So, we're from New Hampshire. We're actually from a metropolitan area of New Hampshire, and we have a picture to prove it over there on the left. So, New Hampshire is known for having a lot of snow, more snow than Washington, D.C., a lot of hills, and a lot of old clocks, and the kind of clocks that don't synchronize with the master clock far, far away, which is just as well because hills generally interfere with the radio signals. We have a lot of places where it's really hard to get any kind of wireless connection to anywhere because the only important point that you can get any line of sight to is the sky. So this is the clock of the Baker Tower at Dartmouth. This is the Baker Berry Library down below. And there is folklore which says that this clock, that the keeper of this clock used to synchronize it with the Dartmouth website by looking at the time on the website, and that the keeper of the Dartmouth website used to set the time on that website by looking at the clock. I don't know if this is true. So, clocks. Old clocks, as most of you probably still remember, tends to drift away from the actual time over time. So they would drift away like 5 minutes per week or something like that per month. They all have different deviations from the real time, but generally we don't get to find out what those deviations are precisely because they don't talk to anything pretty much.
And it turns out that the modern clocks are really no better, except the deviations are in microseconds, mostly. But they are on the microsecond level. But they're really consistent about those deviations. And there are several researchers who actually noticed this and made a really interesting fingerprinting work based on that. Tadayoshi Kono, Andrei Broido, and Casey Claffey. And they started out this entire vein of exploration with fingerprinting individual devices based on their clocks. And so we're going to cover that. But in 30 seconds, this talk is really about using clocks for fingerprinting devices, using clock skews. And the thing about clock skews is that they're there for the asking or for the listening, especially in 802.11 where the timestamp goes in every beacon frame. So you can just sit there and look at your device and look at your beacon frames and fingerprint the devices that's been sending them. And people worked out how to use them, and that's actually where we're scooped to. But we got back at them because we figured out how to spoof them for 802.11 APs. And finally, we're going to talk a little bit about how to detect that sort of spoofing. Okay. So, and this is my official New Hampshire hat. When I heard about the snow here, I figured, yeah, I'll bring it. I'm not going to change. I'm just going to fly like this and step off the plane in it. Except, of course, the plane got canceled. We had to take the train.
We didn't bring our truck. This would have probably been the only car.
Yeah, that's right. Yeah, we're missing that. Okay. So the thing about clock skews is that they are tiny but consistent. And Anya, who's the math part of this effort, will explain how you can actually find them out and graph them.
Well, in the ideal world, all clocks would be perfectly synchronized. In the real world, if you take your reference clock and you graph the other clocks, the time shown on other clocks with regards to that clock, you are going to get something like this. They will all be different. They will be they will be close to, the lines will be close to being straight lines at 45 degrees, which you cannot see on this picture.
You cannot do that. Macs are not our favorite machine.
So you graph the times of other clocks with regards to the reference clock, and you compute the slope by taking the time that another clock runs through. The time in the other clock is going to be delta y when the time is going to increment by delta y when the time in our clock increments by delta x. And the clock skew is defined to be the slope of this -1, because the slope itself is going to be really close to 1. So if you go and graph it, if you go and graph the real numbers, for the colorblind people here, those are actually two graphs. They are so close that they seem to be almost 1. One is green and one is red. So these are points from
one line.
this.
I'm of course colorblind.
Yes. So the time from our reference clock is on the x-axis, and those times are on the y-axis. And we're going to, instead of graphing those actual times, we're going to graph the difference between them and the time in our reference clock, because this will let us get the precision that we need. So if we subtract the time on our reference clock from the time on those clocks, and if we take the results in microseconds, you can see that these two graphs are different.
Yeah,
the red one is actually different from the green one. So these are graphs of times on two different clocks with the reference clock time subtracted. So we just fit the line to the clock, to those points. The slope of that line is defined to be the clock skew. And in parts per million, the actual clocks have this skew in parts per million.
Right. So, just in case you haven't noticed, these are real clocks. And so this little trick lets us actually see that these are two different lines. And they are actually the ring sisses that we've got on the lab. So you can see what the clock skew is in real life. Something like 6 or 7 or 10 parts per million. 10 to the -6, but of course we're going to use this ppm because the superscripts in PowerPoint are way too much work. Anyhow, so who came up with this? Who came up with the observation and used it? Tadayoshi Kono, Andrei Broido, and Casey Claffey in 2005 published this paper on remote physical device fingerprinting. And what they noticed is that different devices had different skews, and those skews just kept consistently at the same levels for different clocks. So you could actually tell a clock by its skew. And the way they did that, they sent ICMP timestamp requests, and they also used TCP timestamp options, type 13, option 8, type 13 code 0 in ICMP. And being very accurate computer scientists, statisticians, hackers, they posed the question very carefully. the question that this fingerprinting was helpful in answering. Namely, if you ask two hosts for their clocks and compute the time skew, are they the same hardware clock? So this is useful when you need to tell two devices that might be one virtualized physical device from each other. And also, this is probably going to be very useful in mapping the clouds, which are all virtualized platforms. But so we haven't seen any people exploring that, but that's definitely something that's going to come up. And it turned out that the clock skews were so consistent that even the network latency could be diffuted with some proper statistics. And this is what the real-world clock skews from their paper, measured on a cluster of desktops, looked like. So you see the hosts ordered by the, okay, help me out here.
By the lowest skew they measured within 12 hours.
So they are arranged by the lowest skew measured within 12 hours, and the height of the bar is the deviation over that time that they observed. Because, of course, the clock skew itself varies a little bit based on things like the temperature, possibly, or maybe power consumption, or maybe any one of those things that you can imagine can affect the physical clock. So the clock skew itself is subject to variation. But even so, you can definitely tell one of the computers on the left from one of the computers on the right. And so, come 2008, we were thinking, well, beacon frames are transmitted 10 times a second, and they have this microsecond clock, and that clock is on the RF interfaces chip. So it's the crystal on the actual card. And this is great because we can just sit there and listen, and we can try to fingerprint the APs. And we said that that's what we're going to do during our talk on fingerprinting access points by throwing garbage frames at them. And guess what? A couple of weeks later, we see this paper by Jana and Casera, published in the scientific conference Mobicom, and it's called "On Fast and Accurate Detection: Unauthorized Wireless Access Points Using Clock Skews." And I go like, darn, scooped. Anyhow, but we start reading this paper, and it turns out that, they can tell an access point from another access point. Presumably, they can tell an access point that is your laptop with one of those cards that let you go into master mode. But they say, this is really good. This is really fast and accurate, and this is really hard to spoof. Here is the timestamp in the beacon. This is what, you'd be able to see it in its 64-bit glory. If you could do that sort of thing, it could be useful, because imagine most of the time you've got a situation when you come in, you open up your laptop, you see some beacons, and the access point that you start dealing with based on what you see in these beacons, even if you do the crypto authentication, that's actually an evil twin kind of a laptop. And you think that crypto protects you, but not so. Crypto is complex, parsing complex data is hard. You start parsing complex data way before you can do any meaningful crypto, and this is your owning a MacBook in 60 seconds talk by Jenny Cash and David Maynard, and then the month of kernel bugs, and there is no driver out there that can be completely relied on to accept complex data and not screw up when parsing it. So wouldn't it be nice to fingerprint a rogue access point before you start interacting with it. And, we can explain this by, drawing a picture with the access points and the Rogue attacker laptop. But let's not do that. Let's go for something more dramatic. Let's have a Star Wars analogy. So here's your station, and you're looking to associate with one of those access points. Yes, and all of those little access points out there. And one of them is actually a rogue access point. Could you hold this is the Imperial March, if you can hear it. Right. And sooner than you know, you're within the tractor beam and you're being served with a nice little layer 2 kernel exploit. And, this is no moon, not really. And the access point goes, too bad. So, thank you. That's enough Star Wars for now. So the idea is then you could use fingerprinting of the access point by timestamps or by any other means, really, before you start accepting more complex data, more complex frames from it, by observing that this thing has a happy clock inside, and it's actually broadcasting that clock. And what you can do is you can just see that it's not the Tatooine that you're looking for, but instead something completely different, a small moon maybe, and desist from approaching any closer. So how can you do that? You can do that by observing that there is a timer on the card, and you can query that timer in your card for the very accurate time stamping of what you're getting, of the frames that you're capturing, beacon frames included. And the reason for that timer, and this is 64-bit and microsecond resolution, is that the clients adjust their timer from this beacon timer to stay in sync with the AP. And the collision of rodents being such a delicate dance with the virtual carrier sensing and all that, that they need to do this. And so your RF chipset actually knows how to synchronize your clock with an external clock. And so we have a high precision set of timestamps to go by. And this is a known fact. And so coming back to this paper that offered the fingerprinting mechanism, they observed that these are approximately the clock skews that you expect to find on your Linksys and your Netgears. We mostly use Arubas at Dartmouth, but the picture looks the same. And so you've got clock skews on the order of maybe 64 to maybe 10 parts per million. And these, of course, vary normally because the clock on the access point itself varies, even its skew varies, and the variation is 0.30, 0.70, so less than 1 part per million. And the clock skews themselves are on the order of 10 to 60, so you can actually measure it quite accurately, and you can be sure that it stays within the same region. The error of measurement is not really that large. Okay. And the conclusion that the paper, a very nice paper, and I urge you to read it if you're interested in this, the conclusion was that spoofing this was very hard. A microsecond clock is a lot better than what you get on your laptop. Microsecond level events are much better than microsecond event resolution, is much better than you can hope to do with your regular system clock. And so what they said was, even if you know a skew that you need to match, then, and if you inject beacons and modify the timestamps in those beacons, even so, you are never fast enough. And in fact, what you're going to get is a variation of 100 parts per million, whereas on the actual clock skew, you would expect 0.3 to 0.7. And so it's very, very hard to fake this with a software RF mode injection, right? So this is really good for the defender, not so good for the attacker. You know, you're given away by your clock. Except it's not exactly so. So the question is, can we spoof clock skews with the cheap hardware, or the not so cheap hardware like a Ubiquiti Atheros card? And there are some interesting things to observe about how actual cards behave. Actual cards, when we put them in monitor mode, after they've been associated with one of our APs, exhibit this interesting behavior. They continue to update their timer as if they stayed associated. So this is what the firmware does. I talked to Joshua Wright and Michael Ostrom and Osman, and they think that this is likely a firmware bug, but whatever it is, we can use it. So what that meant for us is the skew of that AP that the card was associated with before we put it into monitor mode. That skew was a 0, which means that we can actually spoof that skew because we have a timer on the card that's synchronized with this AP, even though we're in monitor mode. And what actually happens if you kill that AP, right? The TSF timer of the card itself switches to its own clock and starts drifting slowly away, which again suggests an interesting firmware piece of logic that may or may not have been meant to be there. But anyhow, Net Wi-Fi driver gives us virtual interfaces. And one of those interfaces can be in station mode, synchronizing itself with an AP of our choice. And the other can be a master mode interface, which will mislead one of those stations into associating with us, even if they are doing some sort of a little skew fingerprinting measurement. And so the question is, can we just get that master virtual interface to emit our spoofing beacons for free, whereas the station interface would do the synchronization? It will look something like this, right? Here is the actual AP, and here is the Atheros card, and here is the station, or the wireless IDS, and it will listen to our beacons, and it will go like, it looks okay. It's one of those skews we know. It's one of those clocks we know and like. And inside, we're going to have a management interface, a managed mode interface. And that managed mode interface will update our TSF timer register. And our virtual AP interface is going to emit beacons synchronized to that clock skew. And it will be indistinguishable for the station from the original AP by that measure. And in reality, I hate Max. In reality, something other than that will take place. So the station will be tricked into communicating with us, and we'll be able to send it a crafted probe response or a crafted authentication response with the attendant crypto and all that. Okay. Pity it doesn't work. And from this point on, the effort became like one of those games of snakes and ladders, right? You see the way to the top, and you kind of start climbing, and then there's a snake, and you're like back to square one. Except in this case, the snakes were fatter, and the ladders were fewer. And actually, this was found out by my student, Kirsil. He discovered that the snakes and ladders game actually came from India, his homeland. And it was an old game that was supposed to teach the children about the virtues and vices. And the virtues lead you up and the vices bring you down. And as such, it was brought over to England and used for the same purpose. And in the end, it ended up in the cereal box. But, this is the snakes and ladders right there. So here's the ladder. Med Wi-Fi already has support for multiple virtual interfaces. And those interfaces can be bridged, so you can have a virtual AP and the virtual station. And it almost looks like it's going to work for free, well, except not quite. The virtualization is not fully virtualized. When we looked in the code, we figured that we found out that first you won't be able to actually create a host AP after the station, after you've done your synchronization. So it only goes into that mode if a station, if the AP is already there. And secondly, you can only run the chip in station mode if you create it as a station. So this is not so great. So that means we need to mess with the driver, and this is what the driver looks like. So the driver may be in the station or the AP mode in and of itself. And in the station mode, it's got a function in the firmware. The card has got a function in the firmware that updates the timer from the beacon timestamp. And this you cannot really, this you don't really need to control from the driver. So this is a firmware thing, it seems. And when you're in the AP mode, it will go inserting timestamps into the beacons that you put in the beacon send queue, and it will keep doing that in and of itself, and so it will use its own clock, not the clock that that the station is receiving. So these two functions are actually divorced in firmware, and it doesn't quite work this way as we hoped. So what we have to do is to patch the driver to give this process a little help. First of all, in both modes, we have this add receive management frame function. And in the AP mode, we have the add beacon send, and we can read and write registers through the HAL functions. And this is what we're going to do to marry those two functionalities. The driver will set it to the operating mode of being an AP. This is, again, a firmware thing. And it will emulate all the other modes, such as the station mode for the virtual interface in software. And so the TSF timer in this AP operating mode is not updated from real AP beacons, whichever beacons you receive. And so we're going to use this wonderful function called a TSF double register write. It's luckily all there. And in the receiving path, when we're receiving a beacon, we are going to insert this little clause here, extracting the timestamp from the beacon received and writing it to the TSF timer register, so that our beacons, when they go out, will have stamp of the good known AP to which we're synchronizing. And again, it sounds great, but it doesn't work, because doing just that breaks beaconing. You start overwriting the TSF register, and something about how beacons are scheduled and pushed out by the beacon send queue is broken. And here is this fat smiling snake, right? But that's okay, because we can nudge it. Right after we've gotten our timestamp from the real AP, we're going to kick the card saying, it's time to send the beacon. And so that will force the beacon transmission. And the TSF timer actually stays overwritten. Okay? And the result is something like this. So one of those colors that I don't see is red. And this is the real AP. And the other color is green, which is what we push out in our faked beacons, right? Or maybe the other way. But anyhow, you can see that one of them kind of follows that line, except every now and then it dips. That's when our synchronization is not fast enough. But that's okay, because the real skew and the spoofed skew they're pretty close. And actually, considering that within a normal clock skew, you expect a 0.30, 0.70 variation. This is within the normal daily variation. So what you see is that, this is a hot day. The clock is behaving a little bit different. That's okay, because it's within the normal variation. And so
what you need to do instead is if you wanted to detect that kind of thing, you would have to detect something called jitter, for which there are different definitions, and it's a sum of deviations from what you would expect, basically, and not the actual skew.
And we'll show up you a picture of that later. But, let's see how far we can take this. What we want is for the client to be misled into mistaking us for that AP, even if it's watching for the clock skews. And it's really easy for the client to watch out for the clock skews, because if you recall, you need no more than a Wireshark and a very, very simple script that does the line fitting and figures out the clock skew. So, unfortunately, the AP, the real AP, may also be heard by the same client. And in that case, timestamps will collide, and the skew will be all screwed up. And we don't want that. But the tail of 8211 channels is that they overlap. And so you can be presenting a stronger signal to the client on a different channel. And clients and drivers actually tend to throw out stuff that you hear on a different channel after you've decided which channel you decide to be associated on. And so what we're going to do is we will choose a neighboring channel to broadcast our signal. And there is a place in the kernel, in the driver, that figures out the channel on which the access point with which you're going to associate is, and it fills it in from the scanning results when it's looking for the stronger signal. And what we are going to do in our driver, of course, is we're going to override it. Because otherwise, we won't be able to occupy these two adjacent channels. And it turns out that there is another place in the management frame receiving path, which basically discards the beacons that come in on a channel other than what you are on. And so in order to receive those beacons from a real access point so that we could synchronize to it, we just need to disable the discarding part. And that we did. And so this is the result stretched to scale so that you could see the deal about this. Again, the real AP is the line that's straight. The spoofed AP is the line that's, well, not really a line, right? But imagine that this line is very, very thick. And so it's, again, pretty much the same slope. It's, again, pretty much coincides with the red line, which is what we're trying to spoof. But unfortunately, there is this extra variation. How much variation is there? Not that much, it turns out. So even though we're missing some beacons because of the silly switching between channels, the real skew of 17.25 gives us a spoofed skew of 16.49. This is the difference on the order of, what, 0.70, the top of the expected variation in one clock skew. And this is, you know, we can do better than that in some cases. This is a difference about 30. Well, that's okay, because again, this is the lower end on what you expect in variation. And we failed this test once by going by having a variation of about 1 ppm right here. Well, yeah, we're unlucky one time out of 4. And so we can still do that, I would say. So the deal with this is how you detect it. So no longer it is okay to just fit a line to the measurement curve. And of course, if I collapse the scale, you will actually see one of those green lines, if that is green. Anyhow, you have to look at the jitter. You have to look at this, whether there is a consistent variation component in there. And you can do that, but it gets kind of hairy because at microsecond intervals, you know, you never know what is your error and what is the behavior of the AP. But you've got to watch out for it, because if you're doing that sort of detection. Well then, this is the picture for the normal beacon interval. 10 beacons per second. And so we can spoof pretty well at that beacon interval. What if we reduce the beacon interval and start sending more beacons? It becomes slightly harder to spoof. What if we start sending twice as many beacons per second, 4 times as many than normal? Then yeah, you can actually tell that something bad is going on because you actually see a lot of jitter. But then, of course, you can increase your beaconing. You can shrink your beaconing interval even further. But then, of course, your network will be all beacons. That's very useful. On the other hand, if you reduce your beacon rate, well, this is where spoofing becomes much, much simpler. Okay, then. So, for conclusions, timestamp measurements are really nice and exciting. It's just there are a number of really interesting papers out there, starting with the classic by Conor Claffey, and continuing to that paper that we slightly adjusted the claim of. That it's a great paper and it's a great piece of work. And you know, even if we were scooped, we were happy that the idea has been put out there. Except, of course, software scheduled injection is not the best that one can do. In fact, if you look into the card, and this is actually what I learned at Shmoocon and at TourCon, is that you really have to know your card. You really have to know your driver. You really have to, and it's great because you can meet all the people who are experts in this, which we're not. And you know, ask them nicely, and they might actually be able to tell you. But you've got to know your card, and if you know your card, you can spoof those things really, really well because the card itself does most of the work for you. It's already helping you a lot. So, nevertheless, if you're paranoid about who you connect to or about what sort of access points are on your network, and you can do a lot of sniffing, which we actually can on Darknet because we have about 200 wireless monitors spread out through the campus, then asking a device, what's the time? What's the time? What's the time? What's the time? Is a good prelude to a closer association. And a good way of, and listening is a good way of finding out what this device might be as opposed to what it's claiming it is. And finally, unfortunately, AP beacon timestamps appear to be spoofable. So if you're building a product based on that, you have to be very careful as to what you measure. A simple line fitting technique would not work. You'll have to watch out for jitter, and maybe, just maybe, you'll have to do something else. And we should all try harder. And of course, you know, we'll be happy to take a look at that once you're done putting in the hard work of developing it. And we're going to post the slides and the patch for what it is. And this is a picture that I was looking for to conclude with the title, "What's the Time, Please?" And this is what Flickr came back with. So apparently this emu wants to associate, but is careful who he deals with. And there is another one out there, I think, doing the same. So, you know, it's looking at the dashboard timer. And is that really this car that I want to be dealing with? Okay. With that, I'll take your questions.
I don't have a question so much as a point. I think that you can get rid of the part of the jitter issues by adding a second register into the driver and having it increment the TSF timestamp by a certain number of milliseconds per.
I'd love to talk about this, right? Yeah, the I okay. So the point is that we could get rid of the jitter by using another register. Now, from what we found out about the card, we could not find. I mean, the register that was there was worked on by firmware and was consulted by firmware. And so we have not found another register that would, it's actually two registers, two 32-bit registers, one 64-bit register. We have not found a way to do this, but I would definitely love to know how. So please, please, please.
Yes, the second part of that is that you're updating that register, but looking at the jitter on the order of 2 microseconds per beacon, that is right around the range of what frequency it's running at. So I would say that if you can stick to the same register, but make that code run in real time, because it appears that there might be 10 clocks being used as a subroutine sometimes, not all the time, after that register is being dumped into the RF.
I fear that we would need to deal with firmware at this level, and we do not have that. We do not have that capability. We would love to. Now, what we tried to do was merely with the driver, and we think of this as a cheap way. I mean, if you can think that ubiquity is cheap, well, I can afford it, right? But like I said, I'd love to talk about this. Any more questions? Yes, please.
What about the beacon rate that you're changing? Can you use that as when you match clocks and you but now the beacon rate is different? Is that something you can continue to fingerprint with?
So it doesn't really matter for the clock skew how many beacons you receive. It's just the accuracy of how you can spoof. So
If I'm the client trying to determine which one I want to associate with, can I use the beacon rate as part of my fingerprint?
well, yes. So we actually never saw a beacon interval different from the default. But certainly, if you find that somebody is beaconing at a rate that's not exactly what you expect from your regular infrastructure AP, that in itself is a dead giveaway. There is a bit of an issue with that, though, because the beacon queue is the lower priority queue, and so sometimes beacons are skipped. So if you look at like inter-beacon intervals, that's not a very good fingerprinting technique we found out. But if you really see an AP beaconing at something other than an accepted and normal infrastructure beaconing rate, yeah.
I was actually thinking your technique where it decreases jitter, you change the
Well, we'd be giving, yes. So we'd probably be able to fake that better if we changed our beaconing interval. On the other hand, we'd be giving ourselves away by the very fact that we don't send 10 beacons per second, but rather a different number on average.
So when you looked at the vendors' products that you looked at, nobody's doing any kind of dynamic beacon interval change? It's all manual?
We have not, what we've seen so far, and we haven't seen much, has been, it's not one of those settings that people think much about. And it's almost always in what we've seen we have a Aruba infrastructure. We used to have a Cisco infrastructure. We still have a Cisco infrastructure in an affiliated medical school. And it seemed to us that no one is actually doing anything much with the beacon interval.
So the variable's exposed to the operator, but nobody's really paying attention.
Yeah, not that we noticed, not that we know of. The original paper proposed this as a WIDS primitive to look out for, and our concentration has been different. Our concentration has been, well, if you're really paranoid, what can you do without your driver being changed to something completely different and being absolutely bulletproof with respect to the data it accepts. So what we were thinking was a driver firewall, really. So we don't let the driver code paths see the data before we have a certain things about the AP. Yes, such as what the times are, because it's hard to screw up parsing that out, that one thing out. And also, we had another effort in which we injected malformed frames going out at the AP. The idea was that there are 8 flags in there in the frame control header, and you can vary them any way you like. They're supposed to be 0, pretty much all of them, on association request, authentication request, on probe request. And the AP may or may not respond to you if you send it a probe request that appears to originate from the wired side. Right? What is that? How did that frame arrive at the interface? Oh, it kind of crawled through the wires. And there is, you've got the toDS bit and the fromDS bit, and they are for your data frames to indicate whether you're sending it to the distribution system or receiving it from the distribution system. And yet, a lot of APs would respond to any old garbage and say, oh, here it is. Here's your probe response. Here's your authentication response. So by the pattern of the malformed frames that you respond to, you can tell the architecture of the AP as well. How are we doing on time?
We're over.
We're over, as usual. Well, thank you very much.